I think we can get started. So welcome everyone to this week Autonomy Talks. This week is a great pleasure to have a talk from Sarah Lee, who is a PhD candidate in aeronautics and astronautics engineering at the University of Washington in Seattle. Something about Sarah. So she received her Bachelor of Science in Engineering Physics from the University of British Columbia. And now her research combines game theory, control, and optimization to enable large-scale autonomy in disruption-prone and human interactive settings. Examples of these settings are urban air mobility, roadways, and automated warehouses. While doing her PhD, she spent some time at ONERA, the French Aerospace Lab, and in the Project Loon at the École Nationale de l'Aviation Civile, and also at Microsoft Research. Today, she's going to talk about sustainable and safe coexistence, talking about large-scale autonomy and resource disruptions. I personally am very excited about the topic. I've been skimming some of her paper, and I really want to see more about that. So I give you the stage, Sarah. Go ahead.
Yeah, thank you, Jill. Resource disruptions. So in a nutshell, I develop in the single agent autonomy that can interact on a fleet level. And I've been motivated to study this kind of autonomy by scenarios rising from air traffic management, urban transportation, collaborative task completion, and warehouse logistics. So in all these settings, autonomous algorithms are typically deployed for individual task completion, but due to the shared operation space and shared resources, individual performances end up being coupled to the fleet behavior. Right. And in my research, I believe that in order for not just one or two, but many autonomous vehicles to successfully operate in this shared space, vehicles need to start considering their fleet level impacts during the individual planning stage. Also, sorry, I forgot to mention this. Please just, if you have any questions, just speak up during the talk and stop me. So for example, let's look at just a UAV tasked with delivering flowers from the warehouse center to a customer living in the suburbs. With adequate perception and knowledge of the city layout, we can use some kind of optimization-based trajectory planning algorithm, such as sequential convex programming, to compute paths that avoid buildings and minimize delivery time. With more unpredictable obstacles, such as, for example, weather, thunderstorms, or moving cyclists, we can use more stochastic planning methods, such as those based on Markov decision process, to provide real-time replanning to help reach the UAV reach the destination. However, I guess here, the goal really isn't to just deliver one flower to the customer in the suburbs as fast as possible. It's really to deliver all the products purchased by a customer demand base in the suburbs in a way that all the purchases are delivered in optimal time. If we simply ran the individual algorithms independently from each other, what could end up happening is UAVs might very well collide into each other as they try to reach similar destinations. If we plan all the trajectories together, considering all the UAV positions, destinations, and possible trajectories, then the problem quickly becomes computationally intractable, and it's not fit for kind of a fleet level planning. Fleet level planning, especially with kind of recently there's kind of rising consumer expectations for their service times. So it turns out this kind of problem exists in many different domains that's facing the adaptation of autonomy at a large scale, including the kind of increasingly busy low Earth orbit in urban spaces, in warehouses, and on the ground in transportation. During my PhD, I focused on this question that's fundamental to enabling large-scale autonomy in all these settings. How can we interface single vehicle planning algorithms in a scalable manner so that a fleet of autonomous vehicles can safely carry out individual tasks in a shared space with resource disruptions? So I've been analyzing problems that arise from leveraging single agent planning algorithms to perform congested stochastic motion planning at scale. And to do this, I take an interdisciplinary approach in my work and combine tools and techniques from game theory, optimization, and control to achieve my research objective. My contributions so far can be categorized into 3 different areas: reducing demand-driven congestion, improving resiliency to resource disruptions, and planning safely under limited coordination. And so today I want to specifically focus on the work on reducing demand-driven congestion and planning safely under limited coordination. So to more concretely formulate this individual trajectory planning problem as an MDP, which is a fundamental model in my research, I want to introduce an air traffic management example. In commercial air traffic management, the complete daily flight plan is generated weeks prior to the execution of the flight plan on the actual day. And it's typically based on a mixed integer program that's heavily constrained by many different factors, including plane types, flight level preferences, airlines, weather forecasts, space availability, all of that. And prior to execution, planes receive this kind of plan that's planned with respect to many different factors. And it's just in the form of a sequence of origin and destination pairs denoted by 2 5-letter codes, which is shown here. The flight level that these transitions should happen at, which is typically, also given, as well as the timestamp at which these planes should be making these transitions. So at real-time execution, which is typically referred to as the tactical planning stage, uncertain variables like weather and delays become non-trivial and can't be, considered or handled through that pre-existing flight plan. So in this setting, we take a flight-centric perspective and assume that each plane is solving a finite horizon Markov decision process involving states, actions, transition dynamics, and costs. Here, the state models the physical airspace and is given by a discrete set of available waypoints that air traffic management uses to denote the space and the flight levels. At each state, there is a discrete number of actions that correspond to the reachable neighboring states of the current state. And these actions in MDP can result in non-deterministic outcomes. For example, if we're trying to take off a plane at 1 p.m., it might still mean that by 1:15, we're still stuck on the runway, lining up for the runway. So the cost of the MDP is constructed based on the pre-existing plan. For example, so that the resulting policy would follow this pre-existing plan in expectation. So for every time-space deviation away from the flight plan, we incur additional penalty. So for example here, if the plane's original plan is to follow kind of this lower set of waypoints to its destination, then the MDP costs are such that at these waypoints at the right times, they are a cost of 0. And then for one step away from these optimal states that the plane should be at, we incur some cost of 1, and then further away 2, and so on. So then the MDP objective is to choose the actions at each state that minimizes the expected state action cost for the plane over this finite horizon period. The mapping between states and actions is the policy pi, and the goal of the MDP is to find this optimal policy pi that basically selects all the optimal actions to achieve the best expected cost. In expectation, the output of this MDP is just exactly what the planned trajectory should be. Finally, since MDPs are stochastic planning models, we no longer assume that the flights will follow a deterministic path, so that an optimal action is generated for all relevant waypoints and flight levels of this plane. And on the left here, we have a simulation of this MDP model ran for a 2.5-hour period in July 2017 for flights leaving Paris. And so in this model, we can incorporate the 3 existing air traffic control methods that are used to reduce congestion during technical planning. And these are 1, redirecting flights to different waypoints, 2, delaying takeoff and prolonging landing times with respect to the congestion in the sky, and 3, changing the predetermined flight levels. So that's for 1 flight during a disruptive event. When there are multiple flights sharing the airspace, their flight plans interfere with each other, and so must be considered together when we're rerouting. And the main separation, and so the main constraints here are typically separation constraints for the planes. And the main ones here are requiring minimum vertical and radial space from each plane, as well as requiring a maximum capacity for different sectors of the airspace. So here, just as an example, I've shown the airspaces over France for different flight levels. So suppose let's say we only have 2 planes, this green plane and red plane in the sky. Because of the existence of a red plane and where it is in the airspace, the green plane's optimal policy will now depend on what the red plane is doing. So it's not super clear what the best policy then would be for both planes. And this is where game theory comes into play. In game theory, the goal is to find an equilibrium, which is a joint policy for both planes that's optimal in some sense from each plane's perspective, their own perspective. And so there are multiple equilibrium definitions in game theory. Here we're using the Nash equilibrium to define optimality. And so at Nash equilibrium, which is the kind of like both players' policies, both players achieve kind of the optimal performance when you assume their opponent's policy is fixed. In this case, the Nash equilibrium is player 1, the green plane and the red plane's policies, where when it simultaneously occurs that they're able to stick to their pre-existing plan as much as possible, despite the constraints imposed by the other plane's presence. And so mathematically, the 2 planes are really solving these 2 optimization problems, where plane 1 is optimizing over its policy and its transition dynamics for itself, and the expected costs which depend on the other plane. And similarly for plane 2. And at Nash equilibrium, where the policies achieve that when we fix policy for the red plane, policy 2, the optimal solution, policy 1 is the optimal solution to 1. And when we fix policy 1, policy 2 is the optimal solution to 2. So you can see maybe kind of graphically what happens is then planes do not touch each other during the flight, and they can each go to their desired destination. So you may notice that I didn't actually explicitly state how their policies are actually affecting each other. So how the planes MDPs are coupled, really. So to couple them, I'm using a model called Markov decision process congestion games. And this model is a type of stochastic game that couples individual MDPs to the joint state action probability distribution for all players. And in my research, this game is applied to many different settings, including urban air mobility, warehouse trajectory planning, and competitive ride-hail routing. And to kind of more mathematically define how they become coupled, I'll just use a warehouse robot example. So consider the scenario in the warehouse where we have multiple robots who are collectively planning out their paths together to pick up packages when the customer packages arrive. However, at the time of planning, the package arrival is, we don't know when it's going to arrive, and we can only model it as some probability distribution. So then each robot's goal is to traverse the shared work floor and pick up the package at the lower level when they arrive, and then drop them off at the top row. So modeled as an MDP congestion game, each robot essentially solves the single agent MDP problem where with the same kind of state action transition definitions as the one I showed previously in the air traffic example. In addition to the standard policy variable for an MDP, we now introduce the state action probability distribution for each player given by xi. And so xi at state S and action A is the probability of robot I or player I being in state S and taking action A. So typically in MDP literature, this is also referred to as the occupation measure. And each robot's MDP then is coupled to their opponent's policies through their state action probability. So how this works is the following. Suppose player 2, which is in the middle, and player 3 have chosen their trajectories as the following. Player 2 is going down to the purple pickup location, and player 3 is going to the green one in this route that's drawn here. What player 1 sees, or how player 1 is affected, is effectively he sees this moving wall of costs, this like moving cost, moving MDP cost that results from player 2 and player 3's chosen trajectories. And that is the congestion cost he will see, and he will kind of consider as he's solving his own MDP problem. So specifically, if each player has some original task completion problem, so here it could be just 0 everywhere and 1 or -1 at the pickup spots, then we're adding on this congestion cost that's dependent on the other players' trajectories and their state action distribution. So as opposed to most stochastic games where the coupling occurs over the policies, here they're occurring over the state action distributions. And doing this allows us to really more explicitly enforce collision avoidance type constraints because we're directly dealing with the probability distribution of a player being in any state. So when a player I's cost takes on that form L, which is shown in the previous slide, player's MDP problem becomes this minimization problem over its own state action distribution. Here, the minimization variable is xi, which is the state action probability distribution, and it's confined to be with a feasible one that's defined by the initial probability, the state distribution at time 0 for the MDP, and the transition dynamics of the MDP, which is given by P. So minimizing over the state of feasible state action distributions, players are solving this objective with a integral objective shown here, which is the player potential. So to compare and contrast this MDP with kind of the standard linear programming form of MDP, we notice that the policy is no longer here. So we're no longer optimizing over the policy. But because the state action probability distribution implicitly embeds the policy in it, we can actually derive the policy once we find out what the optimal state action distribution is. The second difference is that the objective is no longer a linear function over the policy or the state action probability distribution, but it's now this kind of nonlinear integral over them. So I guess what we can say is that if these congestion costs are constant, so like in the standard case, if there's no congestion, they're always constant with regards to opponent player strategies, then this integral just evaluates to a linear function of each player's state action distribution. However, if there are dependencies on opponents' probability distributions, then this cost, when you integrate it, becomes a nonlinear function. So the reason why we switched to this integral form is so that when we take the KKT condition of the previous optimization problem, we can recover this Bellman-like equation to compute the expected cost to go at each state action. And this cost to go is very similarly defined as kind of the standard dynamic programming. At the final time step t, the expected cost to go for each state action is just the immediately incurred cost for the state action, which is given by, now it's given by a congestion cost that's dependent on all players' probability distributions. And then in the previous time steps, in all previous time steps, it depends on the incurred congestion cost and the expected kind of cost to go, assuming that in the future, the player will act optimally by choosing the minimum, choosing the action with the minimum expected cost. So kind of unlike the standard Q-value iterations or dynamic programming, here, the costs or like the incurred cost will change as a function of what the opponents are doing. And so using this kind of Q-value formulation, we can formulate like the optimality conditions in a similar fashion as the standard MDP problems. So, but again, once again, because it depends on other, depends on the opponent's policies, it must be defined with respect to the opponent's strategies. So if we denote, so for player I, if we denote their opponent strategies or state action distributions as x negative I, then if we hold x negative I, so holding the opponent's strategies fixed, player I's state action distribution xi is optimal whenever player I has, whenever player I has some positive probability of taking action A in state S at time t. This means that the corresponding Q-value function at the state action is the minimum Q-value function among all available actions in the state at this time. And I guess if all players have achieved this at some joint set of state action distributions, then we've achieved a Nash equilibrium. So if you recall, many of the applications that I'm interested in involve a very large number of vehicles. So the crucial drawback of games is that they're typically equivalent to solving a coupled optimization problem. And the number of optimization problems is correlated to the number of players you have in the game. So when the number of players increase, the joint policy space quickly explodes, and finding the Nash equilibrium can become intractable. So in my research, I try to simplify these modeling assumptions without sacrificing the model's capability at modeling these applications that I'm driven by. In particular, I found that by introducing a congestion distribution variable y, and requiring that each player's congestion costs are increasing functions of this congestion distribution, I can solve the game as a single optimization problem. So here, the congestion distribution y is basically a weighted sum of all the individual state action distributions. We scale it by a factor alpha to allow heterogeneity among the vehicles so that robots, when they're larger or demand more space usage, will contribute more to the congestion. But effectively, this is, it corresponds to kind of the congestion patterns over the shared MDP state action space. As a single optimization problem, I can formulate a distributed gradient descent algorithm that leverages existing dynamic programming approaches to finding the game's Nash equilibrium. To summarize this algorithm, what we're essentially doing is at every time step or at every iteration of the algorithm, players will choose some policy that they started with, let's say. From that, we can compute kind of y, which is the total congestion distribution, and then evaluate the reward or like the cost of this, the cost of this congestion distribution. Treating this cost or reward as a constant, we can then solve Each player will then solve their own individual MDP. Just the standard MDP, you can solve it using dynamic programming, you can solve it using learning approaches, but the output is basically whatever kind of the optimal state action distribution for this MDP at this reward RK. Then we combine them to formulate the next congestion distribution, and all players then take a gradient step towards kind of the optimal solution from this time step. And if we keep doing this with a decreasing step size, then we can show that this algorithm, all players will converge eventually to the optimal state action distribution for themselves in this game. So this is a significant improvement from the exponential complexities for a general stochastic game, because now each player is solving a MDP problem that's constant with increasing number of players, and the total optimization complexity is linear with increasing number of players. So in the warehouse robot scenario, the resulting paths look something like this. During planning, the robots only know the likelihood of packages arriving at any time instance. And despite this, they can still generate paths that avoid each other and minimizes the chances of collision. Are there any questions up until now? Everyone's good. Okay. So to demonstrate this on a higher fidelity model, I built an MDP model for ride-hail drivers competing for rider demands using data from the Taxi and Limousine Commission for New York City and Manhattan. And in this MDP model, drivers will circle around the zones of Manhattan, which are shown here, waiting to pick up riders or go to a neighboring zone to hope for better chances there. If a driver picks up a rider in any of the zones, then the drivers enter a queue for the rider's destination state, which the queue level would then depend on how far this destination state is from where the driver picked up the rider. And so here the chances of picking up a rider is stochastic, or it's probabilistic. And each driver's objective is to maximize their expected earnings in a finite period of time. If you take a closer look at kind of the optimal distribution of the drivers when in this model, you'll see that they end up swamping kind of these 4 heavily congested zones where there's a lot of ride demand, which is good for the drivers. So the drivers do this because that's their optimal strategy. When they do this, they're earning kind of the maximum amount of earnings with respect to what the other players are doing. But what it means for the riders in the remote zones is that they might have to wait longer for their ride to come, especially for riders maybe in the regions such as like further up the Manhattan in the zone space. So as a ride-hail company might want to consider improving the average rider experience by persuading drivers to kind of spread themselves out more evenly among this urban area. So my solution to do this is to incentivize better driver behavior by enforcing tolls on the driver costs, which are also referred to as rewards here. So by ensuring that driver rewards or cost, it consists of the original congestion cost and a toll value that scales with the last recorded constraint violation, where the constraint is really, we're constraining kind of these more congested zones with the capacity constraint. We don't want the zones to have any more than, let's say, 350 drivers at any point during the MDP process. So by adding on this toll that varies with the magnitude of constraint violation, I can show that there are minimum toll values that exactly enforces any linear constraint on the total driver probability distribution. What's more, we can compute this minimum tolling value without needing to know exactly what the congestion costs are in the first place. And we can do this by just interacting and tolling a group of drivers who are simply playing the game up to some approximation error. So we have a group of drivers who are suboptimal, and we're iteratively tolling them by enforcing some kind of toll value at every time step. And so by doing this, we can compute the minimum tolling value up to the error that is incurred by the players when they try to compute the optimal solution themselves. And if these player approximation errors are constant, then over the whole tolling process, the average constraint violation will converge to zero sublinearly. So my results here borrows from duality and first order gradient descent using inexact gradient oracles. Okay, so let's return to the overarching research objective for a second. My goal is to enable multiple autonomous vehicles to safely share space with one another. And so far, I've assumed that all players can coordinate their planned paths with each other. But often there could be situations where two or more vehicles can't coordinate. So we could have a drone delivering flowers, but it encounters drones that it cannot communicate with for any kind of reason. Maybe they're mismatched communication levels or so on. But not all is lost here. So, knowing the types of these drones, it could still be possible to use basic aerodynamics to approximate these incoming vehicles' trajectories with some uncertainty. And based on my previous work on coupling multiple vehicles' MDPs together, what I can say is that what this kind of approximation generates is some kind of uncertainty in the MDP parameters of the green UAV here. So if we can bound the resulting MDP parameter uncertainty so that they're within a bounded set, or compact set, we can look at the effects of this uncertainty on the drone's performance through how the uncertainty impacts the Bellman operator, which is really the workhorse for dynamic programming and many reinforcement learning algorithms. So the Bellman operator is essentially here, which is kind of the value, what value iteration is based on. You can it takes an input value function vector v, and it computes the kind of another value vector based on taking one step backwards using the Bellman iteration. So if we look at all the possible value function outputs that results from a set of MDP cost uncertainties. So we assume that the MDP cost is now no longer just one single cost at each state action, but a set of costs at each state action. And we look at all the outputs of the Bellman operator given all the different uncertainty in cost, and take their union and look at the resulting value function. Then effectively what happens is we get a set of value functions that corresponds to all the possibilities, all the possible different kind of output performances when we have this cost uncertainty. And so this has inspired me to kind of investigate a generalization of the Bellman operator as a set operator that takes in a set of value functions and then outputs a set of value functions. And what I can prove is that the set Bellman operator, kind of similar to the Bellman operator on the regular vector space, is a contraction operator on the set space with a fixed point set. And what this fixed point set is it's a set of value functions where if you apply the set-based operator to it, it does not change. It's invariant to the set-based operator. It's also invariant to the cost uncertainties that exist for this green UAV. And what's more, we can say that if you start with any value function set, any compact value function set, and you put it through the set-based Bellman operator, asymptotically, all of these iterations, which I'll call like a set-based value iteration, will converge to this invariant set that's invariant to the cost uncertainty that exists. So I went even further and then showed that beyond Bellman operators, this similar kind of type of results holds for a larger class of contraction operators for Markov decision processes, as well as many reinforcement learning algorithms. So examples are for sure the Bellman operator, the policy operator, where we're just evaluating the expected cost to go for a policy. And what I'm hoping to show soon in my work is that this also holds for example, Q-learning operators, which is a contraction operator on the space of state action values. So essentially, we can characterize these operators by three properties. So we can treat these operators on a more abstract level as a function h, where it takes in a value function from the space of takes in a value function from this finite vector space. It takes in a cost, MDP cost, from this set of possible state action costs for this MDP, and it takes in a transition kernel, and then it outputs another value function. Another value function. So if this operator is contracting on the set of value functions, so that when you take two value functions and we apply this operator to it, their outputs are closer in distance than before. If this value operator is order preserving, so if we take two value operators that are strictly, that follows this order, strict ordering, so V2 here is strictly greater than V1, and we apply this value operator to it, then the output is still order preserving. So the output of V2's value operator is still greater than V1's. And if this value operator satisfies Lipschitzness on the parameter space, so if we look at fixing now the value function and changing the MDP parameters, such as cost and transition kernel, the output of the value operator can be, the distance between the outputs of the value operators can be bounded by the distance between the original changes in MDP parameter. Then we can say that all of the previous results hold, and for this particular value operator, there's an invariance, there's a fixed point set of value functions that's invariant to some compact set of MDP parameter uncertainty. So this result generalizes some of the existing robust dynamic programming results to beyond Bellman operator, and it provides an alternate set-based proof for standard robust MDP results. So when I apply this set-based value operator idea to robust dynamic programming, we can gain greater insights about kind of what each different policies are doing. For example, if we look at the invariant value function set under some MDP parameter uncertainty, when we use the robust policy, so this is a policy in robust dynamic programming that achieves the best worst case performance, and then we compare it to the optimistic policy's invariant set. The optimistic policy is the one that in robust dynamic programming achieves the best case performance. And then we compare it to the fixed point set of the Bellman operator that I derived previously. What we can show is that the optimistic policy's fixed point set matches the Bellman operator's fixed point set on the lower bound, and the robust policy's upper bound matches the Bellman operator's upper bound. And so this is pretty intuitive, because we know that the robust policy has the best worst case bound, and optimistic policy has the best optimistic bound. However, through this, we can also show that effectively the robust policy has the least variance of all three policies. so that it actually generates kind of performance that's the most consistent out of all these policies. So yeah, and so far I've kind of have these results for restricted to a single vehicle setting, but I think it will be really exciting to kind of extend these to a game setting where we can where if let's say each UAV is following kind of a robust dynamic programming approach, we can characterize how much trade-off there is between how safe and robust they're being to the uncertainty versus the optimality of the game. Finally, I'd just like to mention a couple future directions that I'm also excited about. The first is extending the game formulation of this multi-vehicle path planning to more complex dynamics, including orbital and urban airspaces. So right now, kind of like the way air traffic control is done for commercial airplanes is manual. So it's done by humans who are monitoring airspaces and then manually kind of avoid collisions between different flights. However, as we kind of migrate towards UAVs and more diversity in the kind of aerial vehicles, they're kind of smaller size, they're more diverse dynamics, and their kind of heightened sensitivity to weather are all issues that human controllers fail to manage at scale. And so for large-scale implementations of urban air mobility, it's necessary to have an automated routing capability to real-time reroute some of these UAVs and perform fleet-level management, which I think with this game-based framework, it's perfectly for this task. Space is another really exciting area for large-scale autonomy, kind of as we accelerate the speed at which we're launching satellites into space, into the same kind of orbits that we have. Like we are not going to get any more orbits than what we have right now. We'll soon need to either clean up or perform on-orbit maintenance of the existing satellites because they will break down eventually and they're taking up kind of valuable orbit space. So an existing solution is to have these space tugs, these kind of very energy efficient spacecrafts to service or deorbit some of the satellites that need maintenance. Here, the complexity of the orbital dynamics, the scarcity of the available resources, and kind of the slow-moving nature of these space tugs mean that if we want to be able to respond to maintenance requests from existing satellites in a timely manner, we'll need to kind of predictably place these space tugs in the right orbits because they also move very slowly. And so with the ability to plan with respect to forecast, data-driven forecast, I think the MDP congestion framework could provide the necessary fleet-level planning that could help space tugs respond faster to satellites that need maintenance. Right, and so yeah, that's kind of the end of my presentation. I'd like to acknowledge all the guidance and help I've received throughout these works from my mentors and collaborators, as well as funding from NSF, GCADI, and ANR. So thank you very much.
Thank you, Sarah, for the great talk. Now let's open the stage for questions. You can either post them in the chat and I will read them for you, or you can raise your hand and I can give you the word. Who wants to be the icebreaker? Okay, Dom, go ahead.
I have a kind of a little more technical one. Could you back to slide 26?
Yeah. Let's see. Faster way. Okay. Yep.
So this is really interesting because basically what you're saying is essentially you're able to reduce like the coupled game to an optimization problem, right? Normally that means that the game is potential. Is that different in this MDP setting? Is that how you proved it? There's some potential function that you're descending on, or is there something different going on?
Yeah, no, that's exactly it. So kind of my original formulation was very general. We're just saying there is some dependency on individual players' state action distributions, but by kind of enforcing this congestion distribution, in this kind of weighted way, and then enforcing the congestion costs in this way, I'm basically able to derive like a potential based on this congestion cost.
Okay. Okay. Oh, and I see maybe the trick is that the congestion cost and the state congestion have the same weight, right? If alpha I was different in the state congestion and state action congestion, it would probably break, right?
Yeah, exactly.
Okay.
Yeah, so
Okay.
a huge part of it is the alpha term needing to be the
Okay.
same.
And it has to be exactly the same. Okay, cool.
Yeah.
Okay, good.
Yeah.
That like matches with everything I've seen in like war drops for continuous blah 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 blah. Okay. So it's like essentially this is like a sort of an extension of like an aggregative or like war drop game to this MDP type setting. Okay, cool.
Yeah, exactly. It's just basically extending that to situations where the dynamics MDP.
Okay, cool. Nice. Thank you. And I guess one other small question is I think for the rideshare, it makes a lot of sense why this is a game, right?
Mm-hmm.
That's perfectly clear. For the air traffic control, why a game instead of some centralized authority kind of dictating who goes where when, right? Because I guess in that case, it's theoretically possible for that to happen. Is there any particular reason why a game versus, because I guess if you're proving that it's Pareto, or I guess if you're proving that it's potential, it is Pareto, right? So you are choosing a Pareto solution. But I guess why, is there a reason for this particular one, or a reason why you think it makes sense for it to be a game?
Yeah, so I guess you're asking like, okay, so I guess I feel like the main difference between it being a game versus there being a central authority is that in the game setting, it's more like from an individual perspective, like everybody's doing optimal. Whereas in the central setting, it's like on average, all the planes are like minimizing congestion, right?
Mm-hmm.
Right. So yeah. So I think So I think here it makes. So this is personal opinion, but I think here it makes sense to do a game formulation, because if you think about it, let's say you have like a ton of flights and they're all delayed, like what happened this summer, and so if you think about these flights, right, they're carrying people, and ultimately the passengers are what you want to deliver, right? If we kind of follow a centralized minimization approach, what we can show typically in game theory, we can show is when you compare the central versus competitive equilibriums in the social average, the central like optimal case, there are certain flights that need to be routed through a very kind of like long route to minimize the congestion through the more efficient roadways or flight transitions to ensure that the average congestion is reduced. So this kind of like you can observe it on ground transportation, where to truly optimize the social average, like the average congestion, some flights or some cars might have to take much longer than the others. But if you look at it kind of from the perspective of there's being passengers, taking these planes, if you delay a couple flights so that they're really delayed, I mean, ultimately what that means is the passengers are really delayed, and then maybe their connection flights also have to be delayed. And then you're kind of like not really solving the problem of trying to reduce average congestion, because the planes would just have to, wait for their passengers. Whereas I think in a game setting, so what we can guarantee is that all the flights are going to be optimal for all the customers, so that I guess there's going to be less occurrences where you have these really longly rerouted inefficient routes for some flight that maybe is kind of holding up the rest of the traveling people.
So what you're sort of saying is that the game is maybe more fair, I guess, right? In a way.
Right, exactly. And I think if the goal is to, to make sure everyone gets to where they go on time, I think if individual legs, if you reduce the average in congestion, but individual legs of the travel becomes longer. So that's part of the model. That's part of the game that I can't really model, right? Like the passengers, all right, you can model it, but not in this particular model. But I think that's something that I think motivates this game formulation.
Cool, thank you.
Thanks.
Great, the next in line is John. Go ahead.
Yeah, Hi, Sarah. Actually, Dom asked my one technical question, so I'll ask you another one. If you can flash up slide 34, I did not understand something.
Yeah.
So when you write it like this, the minimum inside the union suggests that when choosing their action, the player already knows what the C is going to be, right? Which is sounds optimistic, because I thought the whole point was that you don't know what the C is going to be, so you have to choose an action that works for all C's. So is that interpretation correct, that you know the uncertainty when you make the decision?
Yeah, right, so in this setting, yeah, I'm assuming, okay, so if you think about like a time varying situation where the cost and transition are varying at every time step, what I'm imagining is like, if the cost will change, but we observe that change, and then we kind of we choose a better action because of that change. So even if that happens, we're still going to have this kind of uncertainty in the value function space. And I guess what you're talking about, like maybe, let's say like in the robust dynamic programming case, what we're doing is we've chosen this policy already, right? And we fixed it, and then we just kind of allow, the cost to vary over time. So that's kind of, that's actually also why I extended to this value operator setting. So here, for the policy operator, if I fix this policy, then I can just let the MDP parameters vary. And that's, this policy operator is how I'm getting the fixed point set for the robust policy.
Since you had the slide before also, how do you get you need Lipschitz, right? But then your Bellman operator has a minimum in it, which is sort of linear in the parameters. So how do you get Lipschitz with, don't you get discontinuous discontinuities in this, in the operator?
So I guess the Lipschitzness is with respect to C and P. So like for two different values of C and P, the output is Lipschitz. And there is discontinuity in the action, but I guess it's it's part of like the dimension, right? Yeah.
No, I understood that. Thanks.
Thank you.
Great. So we have a question from Edzat. Go ahead.
Can you hear me?
Yeah. Hi, Edzat.
Hi. Thank you for the talk. I have a follow-up question on DOMS relating to the game theoretic solution being more fair, let's say, than a centralized solution. Have you observed cases where there are multiple equilibria? Because we've studied similar settings where the trajectory planning of vehicles, and there are typically multiple equilibria that end up depending on somewhat who plays first. So so the equilibria could be quite unfair depending on who plays first. And
wait, sorry. Wait, sorry. Let me pull up a slide that I think maybe I can use to talk about this more specifically. So yeah, kind of like here, right? Like if you have two planes, I guess so if I enforce that the costs are strictly increasing, there is a unique Nash equilibrium, but it's a distribution for both players, right? So then I can think about then how do I divide up this Nash equilibrium between the two players? Is that kind of what you're saying? Like, given a Nash equilibrium, like, like.
So what I'm saying is more like I can see two equilibria on this graph. One where the green plane is the one that takes its original route and the red plane goes around. So given that and the other one is this one. So basically, whoever ends up yielding, you can have an equilibrium where one yields and the other doesn't, and vice versa. Do you observe that, or is there structure in your problem that makes the equilibrium unique?
No, yeah, that's definitely something I've observed as well. So I guess, okay, so in this game setting, what the Nash equilibrium kind of like comes out as a probability distribution, kind of like almost like, yeah, the sum probability distribution for these planes. So on that level, I can say it's unique in this form, which means like if you like, let's say you sum up these two planes and you look at the total probability distribution, there's a unique one. But how do you divide up this distribution among the planes is definitely something like divide this depending on how I choose to allocate this equilibrium mass to each player. I get different, I get different Nash equilibria. And that's actually something I'm really interested in kind of looking at more, because I think, especially for these flights, it's more useful to generate kind of like as I'm dividing up the Nash equilibria between different planes, to generate deterministic policies. So policy that's not like mixed, so that like, you know, the plane, when it gets to point A, it's gonna be like, definitely it'll try to go in this direction all the time. And I think that so that's actually something I'm trying to work on as well for future work, is look at how can I modify like the distributed algorithm I have to make it more, to generate more deterministic policies for the players.
Okay, thank you.
Thanks.
All right, the next question is from Florian.
Hey, Sarah. First, a
Florian.
clarification quickly. As far as understood, the things you showed us, they were all computed offline, meaning you would get sensor data, you run the constructive operators, you get the solution. Is that right?
Yeah, so the simulations I am running are all based on like data that I already have offline. Yeah.
Yes, but what I meant is how could you make this problem set a little more online? That is, go either into online algorithms or using receding horizon implementations. Do you have any thoughts on that?
Yeah, definitely. So I mean, these, you know, algorithms are offline. Hold on, sorry. Let me pull up a good slide to demonstrate this. Yeah, so for example here, right, this is an offline algorithm, and but I guess the saving grace is that I'm using kind of a finite horizon MDP formulation, and so I think this could easily be extended to MPC settings, where you kind of iteratively run this kind of algorithm for a finite horizon, and then take the optimal action you get every time step, but then in the next time step, like update. And what the updates would be like these forecasted costs. So right now I'm kind of computing these, like these costs represent, you know, the reaching a target, but also the weather forecast. But in an MPC setting, that kind of weather disrupted cost could be updated as we can update MPC, and then in like an iterative way, and then generate like a policy that way.
I see. Did you ever try this out in simulation, whether it works?
I've not tried it out. That's kind of idea I've thought about, but I haven't actually tried out yet.
All right. Okay. Thank you.
Thanks.
All right. Is there any other question? I see Edzat has still the hand up, but I think
no,
it's...
that's the old hand. I don't know.
Okay.
Sorry.
It's your old hand.
Oh, lower hand, sorry. Yeah.
Okay. Is there any other question from the audience? All right, doesn't seem so. I think you were leaving your email address somewhere. I saw it on a slide.
Oh yeah.
If people want to reach out for deeper questions.
Yeah, sarahlee@uw.edu.
Great.
Please reach out if you have more questions. Thanks.
Great. Thank you very much, Sarah, again for the great talk. Wish you good luck for the next steps. And
thank you.
Thank you.
Thanks for having me.
And thank you all for participating. See you all next week for the next Autonomy Talk. Bye.
Thank you, Sarah.
Thank you.
Bye. Thanks.
Bye.